Greetings, physics enthusiasts. Today, I want to talk about something called center of mass. That is the big topic I'm going to talk about today. AP Physics 1, Unit 5, Lesson 4. And we're going to talk about center, make that an E, center of mass. But before we talk about center of mass, I'm going to need to talk about the system and the surroundings. So, the system in science is the thing that we're considering, the thing that we're paying attention to, the thing that we're thinking about. And the surroundings is everything else. Now, there is not really a right answer to the question, well, what's the system and what's the surroundings? It can be whatever you want. You can choose what the system is, and therefore anything that you've not chosen is the surroundings. But there are more helpful choices regarding what the system is that make your life easier. So my little joke is, the system is what we're thinking about, and the surroundings is what we neglect. So by definition, if the system is what we're thinking about, the system always includes Krispy Kreme donuts, because we're always thinking about donuts, right? Anyway, ha ha ha. So let's just think of a couple examples of stuff that we've done before. I'm going to just grab materials. I'm grabbing materials off screen, and now we're back on screen. So look over here at me. Oh, we could look over here. So let's say there's a couple of tennis balls. There's the one with the letters on it and the one without. So we say that there is a law of conservation of momentum. So this ball's momentum is conserved. That's the law of conservation of momentum. But we say a system, like this ball with the red on it, has constant momentum. Its momentum is conserved unless it is acted on by an outside force. Boom. So this hand acted on it. Now this ball's momentum is zero. So it seems like, oh, it has momentum. It doesn't have momentum. So for the ball, momentum was not conserved. What if we add something to the system, like this other ball? Well, now, if this ball moves and its momentum changes, it feels like we're breaking the law of conservation of momentum. We're not, don't worry. But now what if this ball comes in? So if my system is just this ball without the red on it, is this ball's momentum conserved? No, this ball's momentum was not zero, and then the green ball's momentum is zero. Whereas the red ball's momentum is zero, and then it's not zero. So this ball's momentum was not conserved in the collision. This ball's momentum was not conserved in the collision. But if I make the system the set of balls, then the total momentum for the system was conserved. So maybe it would be helpful to define the system as the two balls, and then everything else is the surroundings. Does that show you the difference between, does that show you how we want to carefully select what our system is versus what our surroundings is? We could add in a third ball with some black writing on it. So again, is the red ball's momentum conserved? No, because it was zero and now it's not zero. But for the three balls put together, is the momentum conserved? Sure, there's momentum, but then it goes to the red ball, but then it goes to the green ball. So the total momentum for the three ball system was conserved. Was the total momentum for the two ball system conserved? No. Or this two ball system? No. Or this two ball system? No. So pay attention to what the system is and what the surroundings are when you're thinking about collisions. Because a thing's momentum doesn't always stay constant, but a set of things that interact with each other, their total momentum will remain constant. Okay, so that's my system and surroundings thing. So how is that going to be helpful? Why did I talk about that when I said what I really want to talk about is center of mass? The center of mass will have constant motion. I'm going to put this on pause for just a second. And with any luck, that was just a quick little blip. and my pause is over. Someone walked into my classroom. We were talking about center of mass. So a system that is not acted on by anything outside the system. So the system could just be one ball, or the system could be a pair of balls. If they interact with each other, then my system should be the pair. If there's no interacting, then my system should just be the one. A system that is not interacting with anything outside the system should travel in a certain way. So this ball is going to remain at rest or move in constant motion, unless acted on by an outside force. What about these two balls though? Well, the two balls, this is moving, and then it stays at rest and this moves. The center of mass of the system will move at constant speed. So where's the center of mass? There is some location that is the center of mass of this system, and it will move at constant speed. Well, does it make sense if these two have the same mass as each other, that the center of mass is halfway between them? And look at what happens. If this one is at rest, the center of mass is halfway between them, it's halfway between them, it's halfway between them, it's halfway between them. Do you see that the center of mass is moving? In fact, the center of mass is moving at half the speed that this one is moving at. And then they hit, and then the center of mass is moving to the right. Stay halfway between them, halfway between, halfway between, halfway between. So the center of mass will move at a constant speed. Isn't that interesting? So that the center of mass of a system is a location, and that location will behave just like an object would. That location will either stay at rest, or it will continue to move at constant speed. Or if we were in 3 dimensions, this ball would move in a parabola. If I had some kind of fancy thing, like a hammer. I don't have anything. Oh, here's something kind of hammer-like. This pair of scissors. What if I threw this pair of scissors, it would move in a parabola. But if I threw it so that it rotated, the center of mass would be the location that moved in a perfect parabola, and the rest of the scissors would rotate around it. Ooh. So let me show you how to calculate the center of mass. The center of mass is a location. And when I have multiple objects, like the 2 tennis balls, well, the 2 tennis balls should have the same mass as each other, so the center of mass is right in the center. But what if they don't have the same mass as each other? Or what if I've got something like this that's made up of an infinite number, not infinite, but a huge number of little particles? What I'm going to do is I'm going to take each little particle and I'm going to multiply its mass by its distance from some location. I'm going to say someplace is the origin. So if I want to talk about these two, I could call this is 0, and then measure how far it is out to here. That would be x, and then from here to here would be x2 plus m2 x2 plus ... plus mn xn. So however many objects I have, and I'm going to divide by the total of all the masses, m1 plus m2 plus, add them all up, mn. Do you see that the numerator has the unit kilograms for mass, meters for distance? And the denominator has the unit mass, kilograms. So kilograms times meters divided by kilograms is the unit meters, which is a location. So that's how we would find that. A prettier way of writing that using more mathy terminology is sigma. I'm going to add up all the mx's. M, I, X, I, as I goes from 1 to n, divided by the sum of all the masses, mi as I goes from 1 to n. That's just a prettier, simpler way of writing that. So sometimes we want to find the center of mass. So we could do this. And remember, x is the distance from some location that you call 0, that you call the origin. So if I put a 2 kilogram object here and a 4 kilogram object here, where's the center of mass? Well, it's somewhere between them. It's probably closer to the 4 kilogram object. What I could do is I could set down a little meter stick. Oh, look, I have a meter stick. So what if I were to set down the meter stick? I could set the meter stick down here. And let's see what that calculation would look like. I'm going to say this is at a location 7 centimeters. So 2, come on, give me some ink, give me some ink, give me some ink. Okay, 2, goodness gracious. 2, okay, we're going to get a different head. 2 kilograms times 7 centimeters plus 4 kilograms times, let's just call that 16 centimeters, divided by the total mass. 2 plus 4 is 6. And what does that give me? 2 times 7, 2 times 7, plus 4 times 16, all divided by 6. So that gave me 10 and 2/3. 10 and 2/3. 10 and 2/3. So write 10 and 2/3 right here. Kind of looks, let's see, 2 times 7 is 14, plus 4 times 16, plus 4 times 16, all over 6. Let me just redo that. So 2 times 7 is 14, 4 times 16 is 64. 64 plus 14 divided by 6 is 13. I hit the wrong button somehow. 13. That makes more sense. The center of mass is over here, closer to the 4 kilogram object. So I'm just going to put a little asterisk right there. That's the center of mass. What if I had decided to call this the origin? What would the math have looked like then? We're going to get the same location, but now I'm calling this location 6. So I'm going to do some math and the answer should be 6. So watch, 2 times 0, because now this is at a location 0, plus 4 times, what is this location? It's about 9. All divided by 2 plus 4 is 6. 9 times 4 is 36 over 6, which is 6. Look, it's the same location. So when you're doing these center of mass problems, you need a frame of reference. You need a Cartesian coordinate system so that you can name these x's, these distances. But it doesn't matter what frame of reference you use. You could call this 0 and these negative numbers. You're going to get this location as the answer every time you do this. So that is how you find center of mass. And this is the center of mass equation that you'll probably see in books. Now let's do some slightly fun stuff. I'm going to stop sharing my screen so that the picture of me is bigger. Big Davy. So you could look up Veritasium, which is a great website. And the guy on there will show you, he tosses a cane up and down like this. But he says, hey, if you put your fingers underneath something and you bring them together, it turns out that the place where they come together is the center of mass. Look at that, my fingers came together right at 50. And it'll do that if you start at the ends. What if you start not at the ends? You know, this finger over here on the right got a head start. They're still going to come together right there. Oops, that's not that's the inches side. Right there at 50 on the centimeter side. How did that happen? Or, oh my goodness gracious, What if I hang something heavy on the end? What is that going to do to the center of mass? It's going to move the center of mass that direction. So I'm going to put my fingers here and I'm going to slide them together. And when they come together, bam, that's going to be the center of mass. I keep accidentally showing you the not metric side, but that is the center of mass, which is closer to the scissors. Wow. So if I were to tape the scissors here and hurl this thing through the air, so if I took a video, this would be the place that the whole thing spun around. Whereas if I didn't have the scissors on the end, the place that it pivoted or rotated around would be the 50 centimeter mark. So get something long and thin like this. You could get an umbrella. You could get, again, a cane. If somebody has a cane at home, don't break anybody's cane. You can even do it with something little like a pen, but that's kind of boring. You could do it with the bar from a ring stand if you're taking a chemistry class, but play with that. That's a fun center of mass demonstration. And if you want to watch the video that I talked about of that, just Google Veritasium, Veritasium, and there is a person with a doctoral degree, Dr. Muller, in physics education, Dr. Derek Muller. There may be another E there in his name. Anyway, but if you just Google Veritasium center of mass, there's a great video on that. Okay, I'm looking at my notes. So there are some fun things to think about regarding center of mass. In terms of stability, have you ever used a ladder? I used a ladder a lot when I'm getting things down from the garage. I'm going to hit pause for just a second.
Oh, are you?
Hey, me again. People keep walking into my classroom today. I think I was talking about stability, and I think I was about to start talking about a ladder. So a ladder looks like this. And it's got these little rungs, and you're going to stand on the ladder. The important thing about a ladder, let's pretend it just has these two legs. The important thing about a ladder is you want the center of mass to be somewhere between the two legs. If the center of mass is over here, you're like, how the heck would that happen? Well, if someone decided to stand here, and reach over, I don't know how that's a person, but the ladder could fall over. You want to keep the center of mass between the legs. So sometimes when you're standing up, you stand with your feet further apart. That makes you more stable. If you stand with your feet together, you're less stable. So imagine me standing with my feet together and up on my toes. It's harder to balance. But with my feet spread apart, it's easier to balance. Sometimes when I ride public transportation, just because I'm kooky, I think it's fun to stand up rather than be seated. And I don't want to hold on to anything. And as the bus or the train is starting and stopping, I try to balance. And I'm aware of the fact that my center of mass needs to remain between my feet. What if I'm doing yoga? One of my favorite yoga poses is Warrior Three. My back leg is out and my arms are forward. What do you think is true about my center of mass? My center of mass has to be somewhere above the sole of my shoe. So think about that. You're moving so much of your body in front of your shoe. That's why your back leg has to go out. So your center of mass remains over your shoe. Look what happens. I'm going to bend my knee. I know you can't see it, but I bend my knee. Uh-oh. So when I bent my knee over here, that mass wasn't as far away, and that put my center of mass on the front side. So think about that. If you do yoga, Or if you just play around, on the lawn, try balancing on one leg. Your center of mass always has to be over your shoe. Unless you have 2 feet on the ground, then your center of mass can be anywhere between your 2 shoes. All righty. Now I have one video here that I wanted to show you real quick. So I'm gonna pause for a sec while I bring up the video. All right, so here is a YouTube video. Let's see if this works for you. Center of mass trajectory. That's what I was talking about earlier. Center of mass goes in a parabola. This is going to allow you to see the center of mass. See that beautiful parabola? And there you have it. So just to explain what you saw the object flying around like this. And when they put the dot on the center of mass, that center of mass went in a perfect parabola, and the rest of the thing rotated around it. Super cool, I think. I hope you enjoyed that as well. All right, that's my center of mass talk for this week. And sorry about the interruptions. I look forward to seeing you soon in class.